Okay, so good afternoon, everybody. We're going to start for today. What I want to talk about first really quickly is the exam. So it's going to be on February 17th. So you can find this on the syllabus and schedule here. So that's 1 week from today, which means that if you want to prepare well for the exam, you probably want to start studying today and study a little bit each day from now until then. So that's one thing that I've noticed, that students that I've had in the past who have done well in my course have often had the habit of doing a little bit of studying each day rather than trying to cram it all on the last day. So that's my recommendation to you. I posted a practice exam, so I just want to show you really quickly where you can find that and talk about that for a second. So it's on Blackboard. You can click to open here, okay, and this is basically more or less the same kind of format that you're going to get on your exam, okay? So there's going to be an amount of questions. I don't know if there will be 6. There might be less than 6. I'm not sure. But I'll be careful and make sure that I don't give you too many questions that you can't do in the amount of time that we have for our class. So there's 6 questions on the practice exam. This is a little bit long, maybe, for what I would give you in class. So I wouldn't necessarily judge this based on length, but I would definitely judge this based on content, okay? So I'm going to ask questions that are similar to these types of questions, okay? So take a look at the practice exam, and what I recommend you to do is to practice, try to do this exam on your own under what I would call exam conditions. So that means sit down at a desk with the exam, pencil, paper, and calculator, okay? And try to do this exam without using the internet or your textbook or your notes or your friends or any outside help, basically. And that will give you a good idea on whether you know the material well enough to perform well on the exam. So I mentioned just a second ago about calculators. I sent out an email. So I got some anonymous feedback on the survey which said, hey, I really don't get why we're allowed to use the calculator on the homework, and in fact a lot of the homework problems really kind of necessitate the use of a calculator, but we're not allowed to use it on the quizzes and the tests. And I thought, well, that's a very sort of reasonable point to make. So I'm going to adjust my class from here on. So if you want to use a calculator on your quizzes and on your tests, you can, but it needs to be a scientific calculator, okay, or a dummy calculator. It can't be a graphing calculator, okay? So that's the one stipulation that I would make. How do you guys feel about that? Fair enough? Okay, cool. Yes.
Is there like a version of this with the correct answers that we can check?
I'm gonna post a solution onto this. I might do a video. Sometimes I do a video solution guide with some comments. Do you guys want something like that?
Yeah.
Okay, I'll do a video solution then, and I'll also post the document of this solved exam onto Blackboard as well. But I'll do that sometime in the next couple days. I'd advise everybody to try the exam before you go through the guided solution to the exam, because that's going to be the only way that you know whether or not you're ready, really, to take the exam. Was there another question somewhere there? Yeah?
So I know you said the calculators you can use on the test, but is it like a necessity for the test, or will we be fine with that?
Okay, so let me give an example. So for a problem like this one, let's see here. So for question 3, okay, what you're supposed to do is find the, find the break-even quantity, okay? So basically you're selling bananas for like $1 each, but they cost you 25 cents each, and you have a one-time payment of $5,000 to purchase your stand, right? So you want to know how much bananas do I need to sell in order to break even, okay? So in this problem, what it necessitates you to do is the final quantity is going to be something like 5,000 divided by 75 cents or something like that. So if you want to just write on your exam Q equals 5,000 divided by 0.75, okay? you can leave it as that kind of improper fraction. You don't need to simplify. So if you want to do that, then yeah, you could sort of avoid using a calculator. But I'd say probably bring one, because I'm going to design the exam, since you're allowed to use calculators, in a way where I'm not going to pay specific heed to making it very non-calculator friendly. Does that make sense? So my recommendation would be bring a calculator. If you don't have one, borrow one from a friend, or come talk to me. If you really don't have a calculator, I'll find a way to get you one. But don't show up on the exam day and do that. You need to coordinate with me in advance if you need a calculator somehow. Okay, any more questions on the exam? Or on the practice exam? Yeah, one more.
Would a scientific calculator be fine?
Yeah, scientific calculator is fine. Okay, it just needs to not be a graphing calculator. Okay, so if you show up with a calculator and the screen is like this big, that's gonna be a no-go. The screen should be like this big. Okay, you know, just so that you can put in numbers and do calculations and multiplications and these sorts of things and natural logs. Okay, but no, no graphing capability or equation solving capability. Okay, so if you have a question about your calculator, just send me an email with the make and model, or bring it to class and I'll check it for you, okay? But that needs to be done in advance of the actual exam. More questions? Yeah, Brendan?
So you posted about the homework that's due early next week.
Yes.
Do you often grant extensions, or is it advised that we complete it within the time frame?
Right, so I posted a homework. It's on the it's not on Blackboard. It's on Wiley Plus, and it's due on February 15th. Let me go over to this page so that you can see. Okay, so the homework is on section 2.1 and 2.2. So we're going to finish 2.2 today, and then you'll have today, tomorrow, Saturday, Sunday, Monday, and Tuesday to finish this homework, which is 11 questions long. So I think that's sufficient time. If you're really like just got too much going on and there's no way you could possibly meet this deadline, then come talk to me individually. But I think it's a reasonable deadline, and it's important actually that you try these homework problems before the exam, because 2.1 and 2.2 will be on the exam. So doing this homework is gonna be beneficial for you to do this homework before the exam so that you can practice the material that's gonna be on it, okay? Does that answer your question? Okay, if you have a special circumstance, just come talk to me. All right, so let's move on. So we're gonna have office hours today from 3 to 4:30. I had a bunch of people in office hours last time. That was great. What I usually do if I have like multiple students is I'll just go through one by one students, and each student can ask a question in their turn, and then we'll cycle back around. So that was, I think, pretty helpful for those students to get some help on their homework. So if you want help on the practice exam, or you want help on this homework, then please come to office hours. There's also SI sessions. Do you have special SI sessions next week?
I scheduled one for Wednesday. They have not approved it yet, but there is a chance, well, probably, I'm gonna have like a test review session on Wednesday night. That's like 2 hours.
Okay, so probably this Wednesday session, rather than doing an SI session on Thursday after you already had your exam, probably just double up on Wednesday?
Mm-hmm.
Okay, so that's the plan for the SI session. So that's another super useful way to study for the exam. So once again, the exam is going to be 1 week from today on Thursday, February 17th. Practice exam is on Blackboard. I'll post a solution guide soon. Any administrative questions before we start? Okay, I had one more thing to talk about, which was the anonymous feedback I got actually also had another part in it that said that they'd really like to see more examples in class. And I would really love to accommodate that, but I sort of am going to spend a second explaining why I can't really afford to do that. So when you take calculus in high school, okay, you take 2 semesters of calc to learn the material that we're going to learn in this class in 1 semester. And when you're in high school, you meet 5 times a week for an hour, right? Whereas we work for 3 hours per week total, 1 hour, 15 minutes per class. So I have 70% less time in the classroom with you all in order to teach you basically the same amount of material. Okay, so for our purposes, what that means is I really only have time during class to just expose you to the material, okay? And a great deal of your learning and learning how to do problems and learning how to use that material to make inferences is going to be learned individually at home, okay? And if you need that extra guided practice, then that's when you need to come to office hours in the SI sessions, okay? So I know it's an adjustment from high school to college, okay, but this is the way that we learn in college just because, well, your instructors are generally going to be people who, like, teaching this class is going to be like make up a small percentage of what their actual work week looks like, right? So I'd love to spend more time on examples. I'll do as many as I can, but if you're a person who really needs to see that extra examples, you need to become in office hours and SI sessions, okay? Any questions on that? Okay, then I've spent enough time blithering on about that. So let's start for today. So let me remind us what we were talking about last time. So last time we introduced the notion of a derivative, okay? So what we said was, well, if we have a function which is linear, then I know how to express the rate of change of that line, right? And we sort of had a way in which we could describe the rate of change of a function on an interval by using this notion of average rate of change, right? Which was where we just kind of approximated the function by a line and then found the slope of that line, right? Which was okay, but it really described the slope of a function over like a period of time. And the question then was, what if I want to know what is the slope of the function at a particular point? Okay, and the way we did that was by using this instantaneous rate of change process, okay? By which we calculated the average rate of change, okay, over smaller and smaller intervals, okay? And we noticed that when we did that the slopes of these lines were getting very close to the slope of this special line, which we call the tangent line, okay? So the tangent line is the line which just comes in and barely touches our function at one point and goes off. And the special thing about that line is at that particular moment, it's going in the same direction as our function is doing, okay? So rather than trying to say what is the function doing at this point, we can just describe what is this line doing at this point. And we can find the slope of this line through this process by which we kind of have these progressively closer in slope lines which converge to the slope of the line which we care about. Okay, so that was the process that we learned last time, and that was called the derivative, okay? So the slope of that tangent line at this point, okay, the slope was, we called that f prime of a, where this notation is for the derivative. Okay, derivative of f at a. That's another way we would say that, okay? Derivative of f at a. Okay? So this is what we called that instantaneous rate of change. Okay, was there anything else I was talking about? Okay, then we made a slight observation here where we checked when was the derivative going to be positive or negative, right? And we noticed something interesting, which was, well, when the function's kind of going up, then the tangent line will also be going up, and therefore the slope of the tangent line will be positive, and therefore f prime will also be positive, right? And if the function's going down, then the tangent line will also be going down, and thus will have a negative slope. And so since the slope of the tangent line is equal to the derivative, then the derivative too will also be negative. Okay? Okay, any questions on what we covered last time? Okay, if not, then we're going to move on and talk a little bit about, well, we're going to talk more about derivatives, basically. So I'm going to do section 2.2 today. If I have time, I might start section 2.3 as well. We'll see. But let's go ahead and start here. So in section 2.1, we sort of defined this derivative. We said it's the instantaneous rate of change, or it's the slope of f at t equals a. It's also equal to the slope of the tangent line to f of x at, not f of x, I guess it's t in this, f of t at t equals a, okay? Same deal. Okay, so let's just warm up really quickly by reminding ourselves what that really means. We're going to try to estimate the derivative of the function at the following x values. So x equals -2, -1, 0, 1, 2, 3, 4, and 5. Why don't we just do 2 and 0 and 2 and 0 and 3. How about 3? Why not? -2, 0, and 3. That's what we're going to do. Okay, so what we want to know is what is the value of the derivative when x is -2. Okay, so whatever we write in this box is going to be equal to f prime of -2. Now, we know that f prime of -2 is equal to the slope of the tangent line to f of t, or f of x, at x equals a. Okay, so I'm just going to go over until I see where x is equal to -2. That's right here. Okay, so I check where is x equal to -2, and what I want to do is just draw a tangent line. And the way we draw a tangent line is just as follows. Okay, we just want it to be going in the same direction as f is going at that particular moment. So I think it looks something like that, probably. Okay, so it looks like at this point, this is what our tangent line would look like. Okay, it just comes in, barely touches, and it goes off in the same direction. Okay, it goes off in the same direction. And it looks like the slope of this line, well, we just count boxes to see how much did we rise. Well, we went up 1, 2, 3, 4, 5, and we went over 1. So I would say that the slope of that tangent line looks like it's about 5. And therefore, f prime of -2 is 5. Okay? Any questions on that? Yep.
So to solve it, you're basically just drawing a line and where that line crosses the next path.
Yeah, exactly. Well, we're not really solving here, since what we're doing is estimating, right? And the way I can estimate it is I know generally that the slope of the function is going to be equal to the slope of the tangent line. So if I can draw a tangent line, which I think is pretty good, and just find its slope, that would be a good way to estimate the derivative. But this isn't necessarily the process by which we would actually do it, right? So this is just a little bit of guesswork using the graph. Okay, let's check. How about 0? Well, at 0, it looks like we're right here. And I would say it looks like the direction is basically like this, right? Something like that. Does that look right? Maybe more like that. Okay, so that's my tangent line. And all I want to do is I want to check what is the slope of this thing. Okay, well, let's see how far. I'm going to check and see that I don't want to use this point, because this point I'm going to have to use decimals. I'm going to go until I see a point which looks like it's kind of right on a corner, because I like corners because they're whole numbers. So I'm going to do from here all the way down to here. Check what is my rise. My rise, I went down 1, 2, 3, 4. So my rise was -4. And how about my run? Well, my run went 1, 2, 3, 4, 5. So I think the run was 5. So I would say that f prime of 0 is probably about 0.8. Okay, 4/5. negative, of course. Okay? Any questions on this process? We're just estimating here. Yep.
So the direction of the tangent line will depend on exactly where the point is on the other line?
Yeah, so actually what it depends on is what is the direction that we're facing. Okay, so here's what you can be helpful for some students to imagine. Okay, if you imagine that this is a roller coaster, okay, and here you are in your cart on the roller coaster. Okay, here's you, right? On the roller coaster, right? What you want to imagine for the tangent line is think about which direction would you be looking, okay? Would you be looking sort of up as I'm going up the hill, or would I be looking down as I'm going down the hill? So just think about the direction which your little man or woman or non-binary person is facing, right? Just think about which direction you're facing. And that's going to be the same thing as the slope of the tangent line, right? So if I were to draw the tangent line for this point, then it would be parallel to the direction which my little guy is facing, right? It would look like this in this case. Does that make sense? Okay, I think some students really like this roller coaster analogy. It makes it easy to think about, well, which direction am I facing, right, as I go from left to right. Any other questions? Okay, one final quick example we'll do for x equals 3. So what do? I go, x is 0 here, it's 1 here, it's 2 here, it's 3 here. I go down to where I see what is the function doing when x is equal to 3. So I'm interested in what is this point right here, and what's the tangent line? Well, if I imagine myself riding on the roller coaster, I'd kind of be going in this direction at that moment, right? At that particular moment, I'd be going in that direction. Okay, and we just extend it backwards to see what the line looks like. Okay, so it looks something like this. And let's just expand that a little further, see if we can get something which looks nice. That looks pretty good. Okay, so all I want to do is calculate the slope of this line. Well, the slope of this line, I just take any 2 points which are on the line and I calculate the rise over the run. If I go from this point to this point, then my rise was negative 4. That's my delta y. And my delta x is just the run, right? Which in this case was 1, 2, 3, right? So I'd say negative 4/3 for that one. So I could say f prime of 3 is equal to negative 4/3. Okay, or you can make it a decimal or whatever you want. Okay? All right, so just a simple way of checking here. So this is just to solidify your understanding of what the derivative is telling us about a function. It doesn't depend on how high or low the function is. The derivative tells us which direction is the function going. Okay, how quickly is it rising or how quickly is it falling at a given point? That's what the derivative tells us. All right. So, okay, we look at the table in the warm-up, and we're asked, well, does f prime of x appear to be a function of x? Well, if I took just these 3 data points, would you say that f prime of x is a function of x or is not a function of x? Based on these 3 data points. What do we need to check for if we want to check whether something's a function or not? Vertical line test. In other words, we need to check whether there are 2 points with the same x value that have different y values, right? But here all of our x values are different, right? So we're okay. All right, so I would say yes. It does look like a function, and as it turns out, the derivative is a function. Okay? The derivative of a function is another function. Okay, so we can plot the values of the derivative f prime of x that we found here, okay? The way it looks is a little bit funny, okay? So the derivative function, which let me do it in, how about I do it in pink, okay? I'm going to do it in pink. The derivative function is the function whose height, okay, whose height is equal to the slope of this other function. Okay, so this is going to be a little bit wild, but let me just walk you through it nice and slowly, okay? So I know that the slope of this function at the point -2 is equal to 5. So if I want to plot the function f prime of x with pink here, then the height of the derivative function should be 5, okay, at that point. And likewise, at 0, the slope of the red function is -0.08. Sorry, -0.8. So the height of my derivative function when x is equal to 0 should be -0.8. Okay, and then again at 3, the slope of the function should be equal to the height of my derivative function. So since the slope of the function at this point is -4/3, then the height of the derivative function is going to be -4/3, okay, at that point. So 1 1/3, that's what 4/3 is, so a little bit more than 1. Okay, so what would it actually look like if I graphed this? Well, if you take a look at the slopes, as we move this direction, the slopes are decreasing to 0, okay? When we hit this point right here, that's when our derivative is going to pass through the x-axis, right? And then our slopes are negative, getting more negative, up to, I would say, this point 2. Okay, so that's like our minimum, maybe is somewhere here. Okay, and then our slopes get slightly less negative, until the slope is 0 at this point here, right? Which means that the height of the derivative function will be 0 at that x value. Okay, and then the derivative, the slopes get positive, more positive, right? So we're going up then afterwards. So if I were to graph this as a function, it looks kind of like this. It looks kind of like this. Kind of funny. Okay? So this graph is a little bit busy at this point. But, okay, what I'm looking at here is the graph of the derivative function, okay? Highlighted in green. So this graph of this derivative function is a function all on its own. But it tells us something about the red function. It tells us what is the slope of the red function at those x values, okay? So notice how when the derivative is 0, that means that the slope of the tangent line for that x value is horizontal, right? Okay, so this is about the connection between the graph of the derivative and the function itself, okay? So if the function's increasing, the derivative will be positive. If the function's decreasing, then the derivative will be negative, right? And so on and so forth. Any questions about that relationship? I know it's a little bit kind of mind-bending when you first see it. Okay, I think there's some questions on the homework which help you to understand this by checking, well, okay, which graph could be the derivative of this function? Or what could the function look like if this picture is its derivative? Something like that. Okay.
A problem
Yep.
like that would be like kind of like look at each, like basically like kind of do what we do with the table here, or would we, is there like some way to kind of like eyeball it to see like?
So the problem on the homework is like this. They give you this function, and they say, okay, I'm going to give you 4 pictures, and you tell me which one could be the derivative, the graph of the derivative of that function. They give you one which is the derivative, and then they give you one which looks like this, and then they give you one which looks like this, and they give you one which looks like this, and you're supposed to pick the one which could be the graph of the derivative. And you would say, well, I can't pick this graph, surely, because if this was the graph of the derivative, then all of its values are positive. If all the values of the derivative are positive, then the function better be increasing. But this function is decreasing at some spots, so you could rule out that option. Does that make sense?
Okay.
That's how the problems look on the homework. All right, so we kind of just talked about this. So let's fill out this table. This is kind of a useful table which tells us what's happening to the derivative of a function based on whether our function's going up or down. Okay. So let's just think about the first blank here. So we know that f prime is positive on an interval. And that tells us that the function is increasing on that interval. So what do we think about the slope of f in this box here? Slope of f is ... positive, right? Okay, so these three things go together. F is increasing, slope of f is positive, and f prime larger than 0. Okay, next up, we've got slope of f is negative, and f prime is less than 0. Then what would we say about f? F is what on this interval? Yeah, it's decreasing. Okay, and how about if the slope of f is 0? What's our function doing if the slope is 0? Yeah, it's not changing, right? The height is staying the same if the slope is 0. So f is, what's the word we have for that? Constant, that's the one. Okay, and what about f prime? Yeah, that's the only option left, right? We already ruled out f prime being positive and f prime being negative. The only number that's not positive and not negative is, of course, 0. Okay. So great little table here that tells us about how that stuff's going to work. All right. Hang on one second here. Just want to make sure I talk about everything that I wanted to talk about today. Oh yeah, okay. We'll get to that later. All right, so this is an extra problem. Maybe we'll come back and do it if we have time. Time permitting. You'll come back. But this is basically, oh, okay. This is exactly what I was just talking about. Eli? Not Eli. What's your name?
Eli.
It is Eli. Okay, great. So this is exactly what I'm talking about. This could be a question on a quiz or an exam. It says, okay, this is what the graph of g looks like. Which one of these could potentially be the derivative of that picture, right? Well, we literally just did this. I think it should look like this, right? Because the function is initially increasing, which means that the derivative should initially be positive. And then it bottoms out at 0. That's when the slope is 0. That's when the derivative passes through the x-axis. And then it's decreasing for a while, so therefore the derivative should be negative, i.e. beneath the x-axis, up until a certain point where the slope is again 0. And that's the point where the function passes through the x-axis, the derivative function. And then again, our function is increasing in this region, so the derivative function should be above the x-axis. So that's how you do those types of problems. Okay, I know this is a little trippy the first time you see it, so don't worry, practice is going to help you a lot with this. All right, so let's do this problem number 4 here just to really solidify this. So what we want to do is take a look at this function here, and we want to ask ourselves, well, for which values of x is the derivative equal to 0? Now, who can tell me, what does it mean if the derivative's equal to 0 at a point? Then f is constant at that point, right? So if f is constant at that point, then what does it mean about the slope of the tangent line? It's going to be 0, right? Which means that the tangent line will be horizontal. So if I want to answer this question, for which values of x is f prime of x equal to 0, I needed to ask what x values give a horizontal tangent line. I.e., if I'm riding my roller coaster, at what points am I going to be facing directly ahead? Right? If I'm riding my roller coaster, at what points am I going to be facing directly forward? Right? And the only times that happens is when I'm basically at a peak or a valley, right, on my roller coaster. So in this case, I think this happens when x is equal to what? 0.5? And are there any other spots? 3? Yeah, I think 3 also has a horizontal tangent line. And any other spots? Yeah, I guess 2 or, I don't know, maybe right before 2? Yeah, we'll do right before 2 just to be super accurate. So what, 1.8? About 1.8. Actually, that looks kind of like 1.9, doesn't it? I don't know. I'm not a computer. Okay, and I think that's pretty much it, right? All the other spots were either going up or down. All right, great. So next question we're supposed to answer, for which intervals of x is the function increasing? Okay, well, we know visually that the function's increasing when it's going up, right? So I think if we do this in green, okay, we'll do this in green. So we want to find the intervals for which for which f is increasing. Well, we look for the spots where we're going up. I think this is one spot where we're going up. And then we're going down for a while, and then it hits 0. And then we're going up for a little bit. And then we're going down for a bit. So if I wanted to describe the intervals, okay, for increasing, I would say the following. I would say f is increasing for the x values which belong to, and now in this blank I want to write a set. Okay, so remember way back to the first part of class where we talked about sets and intervals. So I want to say x is a member of this set, right? So I'm describing the x values for which, if we plug in x to the function, we get that f is increasing at that point. So on the x-axis, it looks like these green bits, right? So how can I write that? Can anybody help me write it in terms of intervals? Let's start with the first part. 0 to 0.5. How do I write that as an interval? Yeah, and should we use a closed bracket or should we use a parenthesis on 0.5? Can anybody say why they want to use a parenthesis or a bracket? Yeah, bracket is if it's included and parentheses if it's not. Shania?
I would say parentheses because at 0.5, f is equal to 0, so it's not included.
I agree completely. We should use a parentheses here. Why? Because just like Charisma, is that your name? Yeah. Just like Charisma was saying, okay, if we put a bracket here, then that means that 0.5 is in the set, okay? If 0.5 is in the set, then what we are saying is that f is increasing at 0.5. But if we look at the function when x is equal to 0.5, are we going up? No, we're just flat, right? So we're not increasing, we're just not increasing or decreasing at that point. We're constant. Okay, and now what do I need to do? I need to somehow express the other part. So how do I write the rest of this down? Yeah, Clayton?
I said parenthesis like 1.9, comma 3 parenthesis because use the parentheses because you don't want to include 1.9 or 3 because those are both equal to 0.
Yeah, exactly. It's equal to 0 at those 2 points, so I don't include them in the set. And one thing's missing. What goes in the middle? Yeah, union, right? It looks like a big U. That means union, or. Okay, so the way this reads is x is a member of this interval from 0 to 0.5 or the interval from 1.9 to 3. So this just means or. Okay, so that's how we write it down using intervals. Okay, and I'm going to skip C because we already did an example of where we sketched f prime. Okay, why don't we do it? Screw it. All right, let's sketch a picture of what this is going to look like. Maybe we'll use red. Does red work? Yeah, we'll use red. Okay, so we'll sketch this thing in red here. Okay. Oh, one more part we didn't answer about the other part. What can we say about f prime of x for each of these intervals? Well, the slope is positive, so what does that mean for f prime?
It's above the x.
Which means that f prime of x is, yes. For these intervals, f prime of x is equal to the slope. If the function's increasing, then the slope is positive, which means that the derivative is positive, because the derivative is nothing but the slope. Okay, and we also know f is decreasing on the rest of it, right? F is decreasing on the intervals from, let's see, 0.5 to 1.9, excluding, and then also from 3 to, I don't know, 3 to 4 maybe. It doesn't really look like we can see. Or 3 to 3.5. Oopsie. Maybe I'll put a bracket on 3.5, because it looks like it's still decreasing there.
Yeah, how would you know exactly whether to include a bracket or not if the line extends outwards without knowing where the definite point is?
Yeah, I mean, it's kind of ambiguous in this case. So I would accept a parenthesis here. I would also accept 3 comma infinity if you wanted to. But that's not a great answer because you don't really know what's happening to this function afterwards. It could go back up and down again. So from the picture, it looks like we can tell that it's definitely decreasing from 3 to 3.5. You know, no way to really see what's happening after that. All right, so let's sketch the picture of f prime, right? Okay, should f prime start above or beneath the x-axis? Here's something, but I didn't quite catch that. Well, our function, right, is increasing at this point, right? Which means that the slope of the function is positive at this point. So if the derivative is equal to the slope of the function and the slope of the function is positive, then the derivative should also be positive. Okay, so in this case, the derivative is positive initially. Okay, and then what happens to the slope as we move forward? The slope gets ever closer to 0, right? So the slope is 0 at 0.5. We also know the slope is 0 at this point, and the slope is 0 at this point, right? Okay, then what's happening in the middle? From here to here, the function is decreasing, right? The slope gets steadily more negative until we hit this point, and then it looks like the slope starts to get a little bit more positive as we come down into here, right? So the slope gets more and more negative, right, until we hit this point, and then the slope starts to kind of bend in the other direction, right? Which means that the slope is increasing, which means that the derivative function is increasing. Well, it certainly has to increase if it's going to come back to 0, right? Okay, next up, our function is then increasing again for a little while. Okay, so the function becomes briefly positive. up to the point where, oh, it looks like the function starts to, well, the slope of the function starts to decay as we move forward through this section. The slope of the function is going down to 0. So the derivative is then going down to 0 in that region. Okay, and then the function's negative thereafter. So the function should be positive here, but getting smaller. It looks like that. All right? So a bit of a trippy function.
So I'm not really getting like exactly how you're like figuring out like what way to connect the dots.
Sure. So
I decided that from x equals 0 to x equals 0.5, you might like down with it.
sure. So let's just focus on from 0.5 to 1.
Okay.
Why do we go down with the derivative, right? Why does the derivative start at 0 and go down from 0 to 0.5 to 1? Well, the reason is, take a look at the slope. I'm going to take a look at the slope of multiple tangent lines, okay? The first tangent line is this one. Since the slope of this tangent line is 0, the height of the derivative function is therefore 0. Then we take a look at this tangent line here, okay? This tangent line has a negative slope, right? Which means that the height of the derivative should be negative, since the slope of the function is negative at that point, right?
Yeah.
Now let's take a look at, so whatever this slope is, m, say this slope has m1. This is the slope of this red line, okay? Therefore, we go down m1 units, okay? Agree?
So you go down to whatever the slope is.
You go, yeah, exactly. So the height of the derivative function is the slope of the original function. So if I take a look then at this other point, let's use orange. Let's take a look at the tangent line for this point. If I take a look at the tangent line for this point, which slope is more negative, m1 or m2? m2 is more negative. So the height of the derivative function will be more negative at that point. Is that clearing things up?
Yeah.
Gino, you have a question?
So then, why with like from M2 to 1.5? Sorry, from 1 to 1.5. Why does like the derivative go up? If like one before that.
Right. So why does the derivative go up in this region? That's the question. Why does the derivative go up in this region? Well, let's do the same exact process. Okay. I'm going to take an m1 and an m2. Let's take m1 here and m2 maybe over here. Well, if I look at the tangent line at the red point, it looks something like this maybe. If I take a look at a tangent line at the orange point, it's slightly less negative, I guess. You see what I mean? So if I take a look at the slopes here, m1 is more negative than m2 is. It's a little hard to see. You see what I mean, though? If the slope, as we move forward, our pitch is increasing, right? Okay, maybe I should have taken an m value that was a little bit for m2 that was further out. Let me switch the m2 so that that's a little bit more visible. Let's say I take m2 to be right here, right? And the tangent line looks something like this. Okay? At this point, you would agree that the slope of the orange line is less negative than the slope of the red line, right? So therefore, the height of the derivative function at that point, which can be seen here, should be less negative than the height of the derivative function at the other point. Is that making more sense now?
Yeah, I was just confused because like I just saw it as like a perfect diagonal line, so I just didn't know how it became positive. But yes, it's like slightly.
Yeah, I mean, my picture is definitely not perfect, but it's pretty close, right? What I got the important parts right, which is basically I have it that it passes through the x-axis whenever our function becomes has like a horizontal tangent line, right? So that's the important part. And then the other parts, you know, it's close enough. Really, maybe I could have drawn this a little bit more flat in this region and then going up, but you know, it just has to be approximately correct. Yeah, Brendan?
So does the same reasoning apply to why the derivative is pointing downwards between 0 and 0.5?
Yeah, exactly. Okay, the reason that the derivative is decreasing here is because our function's slope is decreasing in this region. Okay, what do I mean by the function's slope is decreasing? I mean if I take points here and I check the tangent lines, then the tangent lines have slopes which are getting smaller as I move from left to right. The slopes of the tangent line are going from being positive to being less positive, and then to at 0.5 the slope is actually 0. So the height of the derivative function does the exact same thing. It starts being positive, and then it gets less positive as we move to the right until it gets to 0 when we hit this point. Okay? So this red curve is describing the slope of the blue curve. Okay? The slope of the blue curve goes from being significantly increasing, so i.e. the slope is significantly positive, down to being horizontal, i.e. the slope is 0. So the height of the derivative function does the exact same thing. It starts being significantly positive, and then it goes down until it gets to 0. All right, it's okay if you're confused by this at first, okay? Take some time to manipulate these on your own before you start to get it more, okay? So let's do some more problems here. Oh, actually, yeah, we're going to start a new section now really quickly. And I think I have time to talk about what I want to talk about in this section, which is basically two things. Okay, so the two things I'm going to talk about in section 2.3 are so-called Leibniz notation. Okay, Leibniz notation, and also tangent line approximation. Okay, or also just finding the equation of a tangent line. Okay, finding the equation of a tangent line. All right. So we're not going to do warm-up problem A. It's just an average rate of change problem. You've done average rate of change probably 100 times by now. If you want to see it worked out, come to office hours. So for Leibniz notation, this is kind of an interesting thing that you might or might not know, that the calculus, I guess, was invented in, I think, the 1600s by two people at the same time. Okay, so two people living in different parts of the earth happened to discover or invent calculus at the same time. And their names were Isaac Newton and Wilhelm Gottfried Leibniz. Right? So Isaac Newton's the guy who the apple fell on his head and then he thought about gravity or whatever, at least according to the story. He also went insane from mercury poisoning later in life, so he's got that going for him. But Leibniz also discovered calculus at the same time somewhere else, okay? So what we've been talking about so far, when we write P prime of W to refer to the derivative of the function P, okay, this is the way that Newton initially wrote down what what he wrote down in terms of the notation for a derivative. But Leibniz came up with a different way of doing it, okay? And his way was slightly different. And what he said was, okay, what we do to take a derivative, what do? We take the rise over the run. We take rise over run over very small intervals. Okay? So what he said was, well, if I take delta y1 over delta x1, and then delta y2 over delta x2, and then delta y3 over delta x3, and we have that delta xn is going to 0, meaning that the width of the interval is getting much smaller as we move forward. So first we do it from like, 1 to 3, and then we do it from like 1 to 2, and then we do it from like 1 to 1.1, and then we do it from 1 to 1.01. So we take these, basically these really small rises over runs. And so he said, well, what am I going to call the number which I get when I take this process as far as it can go? And he called that number dy dx. Okay, so some of you might know that the triangle here is a capital delta for Greek letters. Capital delta as in D. And so if you basically think about a very small change in rise versus a very small change in run, we use the little d and the little d there rather than the capital D and the capital D. Okay, so this is how Leibniz came up with his notation. Okay, so Newton says if we have an equation y equals f of x, then Newton says f prime of x. But Leibniz says dy dx. Okay? So this is basically just the difference. So f prime of 2 then becomes dy dx evaluated at 2. Okay, so this is the only difference. So it's kind of descriptive because basically what it says is I read this basically from top to bottom. It says, the top part says take the derivative of the function y, and then it says with respect to the variable x. So this says take derivative of y, and then this bottom part says with respect to x. Okay? So let's see another example. We've got the power output P of W in megawatts is a function of the wind speed W in miles per hour. So we're supposed to write P prime of W in Leibniz notation. So you'll notice what goes on the top, okay, is the dependent variable, and what goes on the bottom is the independent variable. So what's the independent variable in this example? Well, does the power depend on the wind speed, or does the wind speed depend on the power? The power depends on the wind speed, which means that the power is the dependent variable, which means that the other one is the independent variable, right? So in this case, that's W. So dW goes on the bottom. What goes on the top is dP. Okay, how about the units? What are the units of dP dW? Just megawatts? Yeah, megawatts per mile per hour, I guess, is what it would be. So it would be megawatts, with 2 T's, megawatts per mile per hour. Why? Because W is measured in miles per hour. Power is measured in megawatts, right? So power is measured in megawatts. Wind speed is measured in miles per hour. So in this case, our units are going to be megawatts per mile per hour. Or it could be, I mean, I guess what you could say, if you think about it, you could also say megawatt hours per mile. That would be another way of writing it, because megawatt per mile per hour, right, looks basically like that. So divide by a fraction means multiply by the reciprocal. But that's kind of a weird way of saying it. But I'd also accept something like that on an exam. All right. How much time I got? I got 13 minutes. All right, so that's basically Leibniz notation. I'll use Leibniz notation and Newton notation interchangeably. So sometimes I'll talk about derivatives. I'll write dy dx. Sometimes I'll write f prime of x. It just depends on what the problem is. And usually it also depends on how the problem is given to me. If they tell me that the derivative is dy dx, then I'm going to write dy dx for the rest of the problem, usually, just so I don't get confused. But if you like one over the other, you can use just that one. Just have to convert back and forth. All right, so that's a pretty basic idea. So in the last 13 minutes here, or last 12 minutes now, I want to talk about tangent line approximation. Okay, so we've talked a lot of smack about tangent lines and how to draw them and how to look at them and tell whether they're increasing or decreasing and that sort of thing. But here we're going to actually find out, how do we find the equation of a tangent line, right? We've done all these problems at the start of class where we said, okay, what do I need in order to find the equation of a line? There were 2 things I needed. What were they? The slope of the line and the y-intercept, or otherwise just some other point on the line, right? I need a point on the line, which could be the y-intercept, and I need the slope. Those are the 2 things that I need to know in order to find the tangent line. Okay? So, if I want to come up with just with the equation of a line. So if I want to come up with the tangent line, what I need to write the equation of the tangent line to f of x at x equals a, I need 2 things. The slope and a point. Well, let's think about how this is going to work. If I have a function, okay, and I have a point A, well, let's draw what does the tangent line to this function at x equals a look like. Well, what we've said so far is just that it's the line which comes in and just barely touches our function at this point, right, and then goes on. So, my question is, do we know a point which is on the tangent line? Yeah, it's this point, right? It's the point where it touches the function. We know that point is on the tangent line. So if this is the function f of x, then can you tell me what in general are the coordinates of this point? Yeah, the x value is just a, right? The x value is a. And then how do you find the height of the point? Well, this point is on the graph of f of x. And I get the height of the function at a given point by plugging in the x value into the function. So I take a, I plug it into the function, and that's how I tell how tall this point is. So if I know how tall it is, I know it's f of a. So I know it goes through the point a comma f of a. And how about the slope? The slope of the tangent line, what's that going to be equal to?
Average rate of change.
Not quite. The slope of the tangent line is equal to the instantaneous rate of change. And there's another word we had for that. Yeah, the derivative. The slope of the tangent line is equal to the derivative at that point, right? So the slope of this line is the same as the instantaneous rate of change of f of x at x equals a, which is the same thing as f prime of a. So the slope is f prime of a, the point is a comma f of a. Let's use point slope. Y minus y naught equals m times x minus x naught. So I get y minus f of a equals f prime of a times x minus a. And this is the equation of this line. Okay, just using point slope. So if I move the f of a over to the other side, I get just y equals f prime of a times x minus a. Sorry, I should have done f of a first. So f of a, sorry, plus f prime of a times x minus a. That's how I write it down, okay? And this is what we call t of x, which is the tangent line. Okay, so I want a line which has the slope equal to the slope of the function, and it passes through that point on the function. So all I have to do is use point slope, and I get a very nice formula. So as long as I know what a is, and I know what f is, and I know what f prime is, which is a bit of a question mark right now, but if I know what this number is, then I know what the tangent line formula is. Okay? I know what the formula is.
So is there like an actual way to tell this line f prime of it? Like instead of just using the estimating it, or instead of just saying doing the average rate of change, making it smaller and smaller, is there like an actual equation?
Yes, we're going to get there. So I sort of agree with you in the sense that it seems weird to give this definition before we know how to find f prime of a using a good method. Right now, the only method we have is to do the slopes of these secant lines over smaller and smaller intervals. But that will work in order to find f prime of a, but we're going to learn more sophisticated techniques later on. Okay, but for now, if I were to give you a problem, I'd probably say, it'll probably say something like this. F of 5 is 11,500, and f prime of 5 is 350. So I'll just give you the number, and you plug it in. Okay, that would be something that I would give you right now. But later on, we'll learn more sophisticated techniques for finding derivatives, and we will do that. Okay, so one final thing I want to just mention about the tangent line, okay, is if we have a function, okay, if we have a function, we can approximate the height of the function by the height of the tangent line to that function, as long as our x value is very close to a. Okay? So when x minus a is small, so this number, of course, is the distance from x to a, right? The distance from x to a. So when it's small, f of x is approximately equal to t of x. Okay, so what do I mean? What I mean is, if I don't go too far to the sides, if I stay pretty close, so in this region, x minus a is small. Therefore, the height of the tangent line and the height of the function are very close to one another. So say I have a function, I know what a comma f of a is, but it's very hard for me to calculate what is f of a plus 0.01. Well, I can just do the tangent line approximation and say, well, the height of the blue line is close enough to the height of the red line for the purposes of my calculations. Okay? Any questions on tangent line approximation? Yeah, Eli. Can I what? Sure. So the tangent line is a line, right, which has the same, which goes through this point. And for a brief moment, it's going in the same direction too, right? Which means that when we're very close to this point, the tangent line and the function are doing something very similar, right? So if I want to know what is the height of the red curve, like here, then I can, instead of computing that height, I can compute the height of the blue line and say, well, since I know that the two functions are doing basically the same thing for a short period of time, right, then I can say that the heights are close to one another and just say, well, I think the height of the red line is pretty much the same thing as the height of the blue line. Okay, but of course, if you move further out, the difference becomes much larger. So you need to make sure that you're very close to your point of approximation in order to use this method. All right, that's it for today, everybody. So have a good weekend. Don't forget, there's a homework due on Tuesday and an exam next Thursday. So hope to see you all in office hours. This part?
Yeah, thank you.
Thanks, you too.
Have a good week.
Thanks, you too.